Hey everyone, welcome to Lecture 4 of Week 2, and today we'll be talking about calibrating the geologic timescale. Before we begin this, we're just going to briefly touch on the nature of time, and you'll read a little bit more about this on the top hat page. But the nature of time is really a physical and a philosophical question. So the way that humans really record the passage of time is by creating a standard or a reference. So in the past, and still kind of today, we used to record the passage of events compared to the revolution around the sun. So that would be our year. We revolve around the sun over 1 year. Our months are very similar to our lunar cycles, where our phases of the moon change, and then we measure days by the revolution of the Earth along its axis. So basically, no matter what we're doing when we're trying to create a time scale, we're comparing these events to a standard that is agreed upon by humans. The geologic timescale is no different. So we talked about the geologic timescale in Lesson 1 this week, and I just want to reference that the divisions of the geologic timescale are based on geologically relevant events. So for example, highlighted in the red box here is the Mesozoic. Remember that means middle life, and that's an era in the Phanerozoic eon. This era is bounded by two major extinction events. One, at the end of the Permian, where nearly 97% of marine life went extinct. Marine means ocean. We'll be using that word often in this class. And then the end of the Mesozoic at 66 million years is bounded by that large extinction event that happened when the asteroid hit and destroyed a majority of the dinosaurs. Now on the right-hand side, you'll notice that there's some dates there. So we have today, there's 11.8 thousand years ago is when the Pleistocene ended. And so we have actual dates, but where are those absolute numerical ages actually coming from? So there were many early attempts at estimating the age of the Earth and getting these absolute ages, or ages referenced to a standard. So Charles Darwin was one of these first attempts, and he actually tried to calculate the rate of sedimentation, or the amount of time it would take for sediment to accumulate in the rock layers that we see today. So he took a location and decided he was going to calculate that. Halley, who's also known for Halley's Comet, also tried to make an attempt at this by calculating the time it would take for oceans to become salty. So he assumed that originally all water was fresh, or there was no salt content, and that over time, salt had to accumulate in these large ocean basins. And then finally, Kelvin was another one of these early attempts, and he sought to calculate heat loss from the Earth's core to provide an estimate of the Earth's age. And as you can see on this slide, I've written nope, and that's because most of these attempts are trying to calculate a rate that is not necessarily uniform. So for instance, Darwin's calculation of sedimentation is flawed because sediment does not deposit uniformly throughout the world. There can be environments where a lot of sediment is being deposited under a short period of time, whereas there can be an environment where sediment is being deposited over a much longer time scale. And we can observe those things today. So a reminder that uniformitarianism is something that's necessary when calculating these ages. So something that's really important here is a uniformity of rates, basically. And we can see this in different environments. So for instance, there are some lakes that accumulate what are known as varbs, and these are seasonal differences in the type of sediment that's being deposited in a lake basin. We can see this in the bottom image on the left, right here. These thicker layers are deposited in the summer, so the thick light layers are summer layers, when you're getting high influx of sedimentation because glaciers are melting and bringing coarse sediment to the lake. Whereas these gray bands are winter sedimentation because during the winter, this lake would be iced over if it were near a glacier. And so we get this banding that represents a whole year based off of the change in sediment. We can also see uniform rates or growth bands in other things such as tree rings. So on the image to the right, Each thick band represents spring or early summer growth when there's a productive growth season. And then each very thin band, indicated by the light brown, indicates late summer to fall growth, which is much less, there's less growing during that season because it's less productive. So when we look at that thick band with the thin band, it represents one full year. So we get annual bands in tree rings. And other things do this as well, such as clams or corals. We can see growth lines that are annual. So there are some instances where we do have uniform rates. One of the biggest things that was influential in determining these absolute dates was what I call the isotope revolution. And I say that because isotopes themselves have really taken over in science. And so some names here that are important are Marie Curie and her husband Pierre Curie, and also Henri Becquerel. These are three names, some of the first people that discovered isotopes and radioactive isotopes specifically. So just a little primer here. So when we're thinking about an atom, all atoms have a nucleus, and that nucleus contains protons, which are positively charged, and neutrons, which are neutrally charged. So it doesn't change the charge of the atom. Isotopes are variations of an element with a different number of neutrons in the nucleus. So some way to think of this is that if you have more neutrons in the nucleus, it's slightly heavier, whereas if there's less neutrons in the nucleus, it's a little bit lighter, if you're thinking about it as weight. But some isotopes are radioactive and they can decay. So on the right-hand side here, this is an image demonstrating these isotopes visually. So in the top here, we have protium, which is a hydrogen that has no neutrons in it, just a single proton. We can have deuterium, which has a proton and one neutron. And then we can also have tritium, which is another hydrogen version that has one proton yet again, but now two neutrons. So just to demonstrate that this is a variance of neutrons in the nucleus of an isotope, or of an element. So radiometric dating then is a calculation of an age in years for an Earth material using these radioactive isotopes and their decay products. So a radioactive isotope specifically is any of several variations of the same chemical element with different masses, because they have that different neutron number, whose nuclei are unstable, they decay, and then they emit radiation. So we can think of this as a parent nucleus decaying into a daughter nucleus or a daughter product. So that's visualized on the right here. We have our parent nucleus or parent atom with our protons and neutrons. It emits radiation, which is this alpha particle on the bottom, and then it becomes a daughter nucleus or a daughter product. Now, what's very, very exciting and interesting about this for geologists is that the rate of decay is a spontaneous but statistical process. So we can't predict when a single isotope will decay, but we can predict when about half of them will decay. And this is known as a half-life. So this is visualized here in this image. So we have on the left, these are all parent isotopes in red. So we're starting out with all original parent material. Now after a given amount of time, let's say for this example 100 years, we see that 1/2 of those parent isotopes have now decayed into a daughter product. Now say another 100 years has passed, so 200 years total, we're going to get more of those parent isotopes decaying, so we'll get another half of those parent isotopes decaying, and more daughter products indicated in the blue. You'll read more about the statistical process in Top Hat, but a good example that you might be able to relate to is popcorn actually works in a very similar way. So we cannot predict when one individual kernel will pop, but we can predict when half or all of them will pop. So think about the microwave setting for popcorn. Say your microwave pops popcorn in 2 minutes. Half of those popcorn kernels would probably pop in 1 minute. And then they also never return to their previous state, which is something else they have in common with these radioactive isotopes. So let's just quickly watch this video for a moment. And as you're watching it, try to pick out what kernel you think is going to pop. Okay, so there's our first kernel, there's our second kernel. And likely you probably didn't choose the kernel that popped first. But if we were to watch this video for a certain amount of time, and obviously it's in slow motion, we would be able to predict when about half of those popcorn kernels have popped. Now it's also important to think about what materials can actually be dated, because we want a material that represents the actual age at which that rock itself formed. So for instance, igneous rocks are very good for dating. Igneous rocks form as magma cools, and that means they've heated up to a temperature that locks these isotopes in place and then cooled. And so when we date an igneous rock, we get an actual age of that rock. Similarly, metamorphic rocks are okay for dating. If rocks reach a high enough temperature but don't fully melt, then the temperature resets the rock and the isotopes are locked in place. However, if a high enough temperature is not reached, those isotopes aren't locked in place, so we don't get an age of the actual rock. So you need to be careful when using metamorphic rocks. Sedimentary rocks are specifically bad for dating. These rocks formed from many different weathered grains, so you won't be getting an age of the sedimentary rock itself, but an age of the grain that you dated inside of the sediment rock. This is an exception when you're using radiocarbon dating, which you'll also read more about in Top Hat. So to finish up today with our mini lecture, remember to read the rest of this page to learn more about the ways that we obtain absolute ages for the geologic timescale. Complete all of the participation questions, and then for homework this week, you will have a short worksheet to learn the basics of how to calculate radiometric dates. You'll look at Canvas for those instructions. If you have any questions, as usual, you can come to my office hours on Monday, Wednesday, and Friday at 10 o'clock a.m. via the Zoom link available on Canvas.